Okay, let's roll them. Let's go. Okay, great. Okay, well, sorry I couldn't make the midterm. I heard it was lots of fun. I think you did pretty well. Generally, I guess if you felt, I'm more than happy to talk about that material, because now that material that was covered in the midterm is a given. Okay, I mean, I'm not going to be going back over that anymore. I'm assuming now that you've got that all part of you. We're going to do new stuff, right? And so you had some trouble with some of that material. It didn't make sense to you. You know, come and talk to me in office hours, and we can sort of go over it. I'm more than happy to, because this course, as I mentioned, keeps building, right? The stuff you did earlier on becomes important later on, right? So you never, there's nothing you can just kind of blow off, because it'll come back and it'll get you later. Okay. Okay. So that's point one. But I thought you did pretty good. Yeah, that was pretty well. Two. Okay. Projects. Okay. Projects came in. We're in the usual negotiation period here of, oh, why did I lose points? Okay. So let me tell you how I'm going to deal with that. Okay. There's the, the artistic expression aspect of your project, okay, which was the part about the R and the D was report and design. That was the points I gave you. And the report was just, you know, how well you said something interesting in the in your description of your circuit. Now, what's interesting? It's not obvious. I mean, you know, a lot of you said the obvious thing, and you got a little check. If if you said something was really pretty interesting, okay, something analysis at some point, or some comparisons you did, or just something above and beyond the call of duty, then you got a little plus. If you kind of did a little bit less than the obvious, okay, just kind of didn't do too much, or I couldn't figure out what you were talking about, or it was just too messy, then you got a minus. Okay, now this wasn't a huge part of the percentage. I cut down. I didn't use all 20. That was 25 points to the grade or something like that, but I didn't use that much. I think I used 15 or 10 or something like that. I mean, everybody got 10 of those 25 points. Just no one did so badly that they didn't deserve anything. Okay, so I gave 10 out of 25. Then the others were plus or minus 5 from that nominal value. I think most of you got the check mark. I think there's a few above and a few below. I'm not too inclined to change that. I mean, it was just, I mean, it was kind of a relative value of yours against other people turning them in. So, but if you feel you really were wronged, bring it into me and I'll look at it. But I mean, it was kind of, in order to do that fairly and regrade that, I'd have to look at all the other exams and figure out where you fit in and how you're plus or minus relative to that. That'd be the only fair way to change it. Okay, let me say something so that just won't cause any embarrassment to somebody. I'm more than happy to look at the exams, but when I do a problem, okay, let's say problem 3A, this is where the solutions go. If you see a slash like that across the whole section, okay, what that indicates to me is that was a blank piece of material there. It comes in with all sorts of material written in underneath that slash. I'm going to wonder. So just a little message there. Okay. Anything else? Any comments about the midterm? Too long? Too short? Too long? Think so? Well, it seems like a few of you didn't finish yet. We got 100 or a couple did almost perfect. So to me okay. To me it was not as bad as it could be. I've done way too long sometimes, right? I mean, it was like a year ago it was too short, right? Got complaints. Oh, it was too short. Scores are too high. I can't differentiate myself from everybody else. I was going to do really good, but geez, I'm just as good as everybody else now. So it's tough. Let me tell you. I try. Okay, so maybe a little too long. All right. Yeah, I do notice some blanks like that, and so I know that's not fair. You don't get a chance to show yourself. But the final will be better. Final generally is more time. You got 3 hours there, and we don't just double the midterm, right? It's 50% more than the midterm, let's say, something like that. So you'll certainly have enough time in the final. So any other comments about it? Questions? Projects? Okay, here's a request. For those who got 100 on the projects, would you turn them back into us again, and we will expunge your name and put them on the web so people can see what we thought 100 was, okay, right? So I appreciate it if you do that. I was going to copy them off beforehand, but we didn't do that. So if those who got 100, if you do that for us, and so everybody can sort of look and see what we thought 100 was. The next projects, I'm going to do a couple of things. I know there's a lot of, I saw you guys did a lot of work and working with equations and all this hand analysis and stuff like that. I'm not going to have you do that next time, the next two projects. So that won't be necessary. So it'll be a lot, the reports should be a lot simpler to do. Okay, so we won't have, most of you did a really pretty nice job actually of, really going through all that material. And we'll try to get it down to just a couple of pages, what I'll ask for. We'll think this through, we'll make a little template for you. But just a couple of pages of just some text that describes what your design was about and some aspects of how you did it. So I'll make it a little more clear cut for you so you don't, I know it's hard to figure out. I know you're all trying very hard to do the best you can, and it's hard to figure that out when something so fuzzy as, make it look good to me. I don't know. That's not a very clear definition of, how to write something. So I'll try to make it simpler for you next time in that regard. Okay. Projects will go out this Friday. Okay. Homework's due Friday. It'll be pretty much, I told you already, based on this one, but with frequency response added to it. We'll figure out the figures of merit. There are some people who need partners, okay? So I ask you to put your names on the news group. And I think it's good to do, you learn a lot by working together. at least, okay, you're going to be able to keep the same partners if you want you did last time. So partners of 2, just like before. Okay. Keep the same partners. If you want to change partners, that's fine. But let's everybody, I would request, if you can, everybody try to get a partner. Okay. I mean, a bunch of you did with only one person. I think that's okay, and it's good in a way, but there's actually something else to be learned by having a partner, and that is how to work together. It's you may think, geez, I don't want to do that. I can do a much better job all by myself. I don't want people holding me back, right? Problem is, the rest of your careers, you're going to be working with other people, right? And here's a chance to begin to get some of that experience and how to do it. And it's not going to be easy, and it's going to be situations where you're the person that's leading the way, and sometimes it's going to be maybe the other people you're working with that have more experience or whatever that are leading the way. So here's a pretty, non-confrontatory situation here, right? I mean, you can sort of just begin to figure out how you're going to work with other people. So there is something to be done for that. Okay, so just in and of itself. So that's not, cooperative working is not the main focus of this course, but it actually is an important aspect. I mean, I do find it interesting. I guess it probably comes from the TAs to a certain extent, but I'm sure a lot of you talk together on a design kind of appears that sort of is the design, right? And it kind of is, it kind of spreads through the class, sort of like a fungus or something like that. But that's okay. I don't mind that. I think that's good. I mean, I like you talking to each other and learning what other people have figured out and incorporating it into your own design. So I think that's actually good from this cooperative standpoint, right? I mean, so. Okay. Any other questions, comments? Okay. Frequency response. All right. Nasty stuff. Okay, so what we're going to do, I'll do this inverter problem and do it in a lot of detail, okay? Then we'll do a couple of more. In effect, this is what your project's all about, okay? It really is not much more. This case we're studying right here, the inverter case, is pretty much the one you'll see a lot. Now, the other one that's of interest, of course, is not of course, but the other cases, common gate and common drain. But this is the one that really drives most of your design. It's this very simple inverter and its variations. The CD here, this capacitance that's hanging off the drain, okay, is composed of also, for your projects for homework, the next stage, right? So you have multiple stages going on. So if you have this situation here, right, and so on, right? This capacitance on this node is composed of the capacitance into the next transistor as well as all the parasitics of this transistor. So you just find all the capacitance that's hanging off that node. And of course, if it's going, this one right here is the tricky one, right? Because this is a gain stage, and this is going across the gain stage, and this capacitor gets multiplied. And that's what this whole Miller multiplication thing is. What we'd like to do is get all of this capacitance down into one equivalent, C equivalent. If it's hooking across the gain stage, you can't do that because you can't. That's not the same as going to ground. But our little Miller is a trick, in effect, which allows us to take this complicated case, which is going across the gain stage, and turn it into an equivalent capacitance to ground. And we used to add that to all the other capacitances that are going to ground. You get an equivalent capacitance on that output. And that's what this is all about right here. This is the CD right here. Here's the CGD, CGB, CGS, and so on. Now, when I did this problem right here in the notes, I took out this all-important capacitor. Now, it doesn't mean this is something you can normally do, okay? I took it out here because the math gets so messy if I put it in here. This is not a good reason to make an approximation because the math gets too messy, right? I mean, that's not why you make approximations. And in fact, the CD is generally you do have to keep it in there, okay? All right, and so even without that, I end up with this thing right here, right? And the point I really wanted to show you in this is that this circuit with this capacitor coupling from here to here has a 0 at CGD over G sub m, as well as 2 poles, and the 2 poles that I showed to you were this one and this one. Okay, and if you look at the value of these 2 poles, you can see something here. R in, that's this input resistance. What happens, like in your project, R in is 0 on your first stage. This is something to get used to. If I put a voltage source here, what's the resistance on this node? 0, right? This is a voltage source. A voltage source controls that voltage totally, which means it has 0 impedance to it, 0 resistance to it. So this, in effect, is like a ground. You know, there's no, from any other signal point of view, you can just think of this as it's like a ground. So when we figure out what the capacitance is from, we're looking at this output node, and we're sort of affecting what's the effective output resistance of this node, effective output impedance, okay? Looking back here, what do we see? Well, we see this is going to a ground. When we do output impedance, right, just like we did output resistance, we set all the independent sources to 0. If this is a voltage source, 0 is 0. 0 is a ground. So that means this CGD is just another capacitor to ground. From this, so that's calculating the pole at this node. Looking this way, what's the resistance driving this node from this, driving all this capacitance here? So the voltage divider, right? We have, effectively, if there's a capacitance on this node, CGS, and, plus C Miller from CGD because it's across the gain stage, and this is the R in, or R source, you want to call it. There's a voltage divider here, right? If this resistance here of this voltage divider goes to 0, that voltage just controls this, and there's no voltage division, right? So if this is 0, another way of saying it is the pole goes to infinity because the time constant's 1 over RC, and R is equal to 0, so the pole's at infinity, or you can say there's no voltage division, or however you want to look at it. But if you have a voltage source driving this node, there is no pole there, right, or it's an infinity. What's the resistance driving this node here? Well, the resistance driving this node is going to be, all the resistance on that node will be RL, I guess, going up, and R0 going down. Any resistance in this direction? No, that's infinite that way. So it's going to be RL in parallel with R0. And basically what that's all about is, like I showed you last time, this is kind of R equivalent, all the resistance on that node to ground. And this is all C equivalent, and this is connected to the transistor, right? So in effect, what we're doing is we're finding all the resistance on that node to ground, all the capacitance on that node to ground, and then what we can do is we calculate the impedance on this node, the output resistance on this node. We're just calculating Z out, just like we calculated R out, right? If there's an R0 here, maybe leave that in. So you have R equivalent parallel with R0 and parallel with C equivalent. And if you work that out like I did last time, a parallel combination of R's and C's has a pole at 1 over, let's forget the R0 for a second. Let's say it's included in R equivalent. It'd be 1 over 1 plus J omega R equivalent C equivalent, right? So just like a voltage divider gives you a pole, a parallel combination of R's and C's give you a pole, and at high frequency, what's going on? Z is getting smaller and smaller, right? The impedance of this capacitor is 1 over J omega C. As we go to higher values, this value of the impedance across this capacitor is getting smaller and smaller. Therefore, your gain goes down. And that's what we're talking about when we talk about a pole. So to get all those ideas together, I think you understand what frequency response is all about.
I don't see why CGD doesn't have a Miller effect on it when both voltages are changing on both sides of the capacitor.
It does have a Miller effect, but on this, okay, good question. Thanks for asking.
I mean, from the drain. I understand from the gate.
From the drain tip, okay, but, okay, if this side, if we're doing output resistance, what do we say about our independent sources? 0. So that means that's set to 0. If that's set to 0, then that side of the capacitor is 0. Okay. Any other questions for that? I just ran through a bunch of basic ideas there, right? And that's kind of what frequency response is all about. If you got that. So parallel combination of resistors and capacitors go to lower, at higher frequency, they have a lower magnitude, therefore, and that is described by this one pole roll off, right? And that is what causes the gain to go down, and that's what's caused to have a pole. That's what it's all about. Just we're reducing the size of the output impedance on this node here, or if we have an input resistance here, then it's a voltage divider. So it's voltage dividers and output impedances that are dropping is what's causing the effect. Okay. All right. Now, let me begin to show something to you that's very important. Okay, so now we calculated in gory detail, forgetting the CD for a second, the poles. And here they are, and there's one pole at 1 over Rn times C Miller, so that's the pole effectively at the input to our, so let me kind of make equivalent resistances now. Equivalent, so this is Rn, and this is C Miller plus whatever else, okay. I'm just saying C Miller's plus CGS and so on. So what I'm saying in this approximation here that C Miller is much, much greater than CGS and anything else, okay? So that's kind of why I only end up with C Miller right here, okay? Then we have our output. I guess for this was an RL here, right? And then we have a C equivalent out here, okay? All right. Now, where's my... So since I got rid of the CD on this output, I end up with this R out CGD, okay? And so why is that? So this, it's kind of, this capacitance here was the CGD. You know, this voltage is changing a small amount, and you can kind of calculate this, an effective capacitance here, kind of this reverse Miller thing, is CGD times 1 plus 1 over A. But if the gain's in it all large, this 1 over A is not important. And if the gain's not large, this Miller approximation isn't very good. Okay, right. You can't see it. I can see it just fine. Sorry about that. Okay, so here's what I was talking about here. So here's this CGD from here to the gate is the part of this equivalent output capacitance. Okay, what I'm saying is you can do just like we did. We can get rid of this. We could have an effective C Miller on the input side. You know, C Miller equals CGD times 1 plus A, right? Which A is, and A, that's really A0. It's really the gain, the low frequency gain. This is RL, would be GM times RL in parallel with R0, right? So that would be the low frequency gain of this thing, okay? Actually, that's the magnitude of the negative gain. Okay, so when we do the output, on the output side here, we want all capacitance to ground. Well, we kind of treat this, so the reverse Miller. So this CGD is 1 plus 1 over A. If the gain's large at all, that means a large change here reflects a small change on this node, okay? Well, a small change in that node is like it's a ground, so we just kind of view CGD as just going to ground, okay? So C equivalent's equal to CGD plus anything else on this node. Could be CD, right? Anything else, okay? Now, I did this exact calculation here without the CD out here, because that makes it a cubic, and it's hard to work with. But you can sort of see this part of the term here is the 1 over R out times CGD, so it's exactly this thing I just was talking about, okay? Then there's this other thing, this other term, okay? And we're going to talk about when this gets important. So the question is, which of these is much larger? If this is much larger than this, then you don't care about this term. But what can happen is this term can be very large, okay? And so we're going to see that case in a second here. And when will that get when will this one become important? Well, that's when CGD gets very big. So if CGD gets very large, then this term gets important, right? Because this becomes very small. So we'll look in that limit there. Here's the other pole, Rn times Cg plus Cgd plus 1 plus Gm R out. See, this came with not from the Miller approximation. This is from exactly solving the equations, but you can sort of see it falls out of the exact analysis. Plus R out times Cgd. Now this was something that we didn't get with the Miller approximation. So it's a little bit of an error that we would have if we usually don't include this, okay, when we talk about the Miller approximation. But it's actually sort of there. Okay. So its Miller approximation isn't perfect, and this shows you how much error it has. Now, what are we talking about when I said let's make CGD large? What happens if we add another capacitor across here? And we will do this for stability reasons. So this is actually a very important case. Remember I told you about we had to kill the gain in order to make this thing stable? One way we will kill the gain is by putting an extra capacitor, a compensation capacitor, across from the gate to the drain of some large gain stage. We'll find the largest gain we have in our circuit. We'll put a capacitor across that because that's the place where we can get the most effect of the Miller multiplication effect. I mean, in actual fact, what we will have to do is create a pole at a very low frequency to make these things stable. So it's a little foreshadowing. And I mean, we'll have to create, I mean, as you'll see in your homework, you're getting poles up around 400 megahertz and things like that. We will have to add an extra pole in, or make one pole, move it around, so that it's down on the order of 1 megahertz. Things like that. Maybe even 100 hertz. So it may sound weird, okay? Here we're trying to make the circuit go really fast, but I'm telling you we're going to have to add one pole in at a very low frequency. Take my word for it for a while. This is a good idea, okay? Bottom line is, the reason you have to do this is you got to make it stable, and when you put it into feedback, this extra pole that we put in at very low frequency, essentially is kind of moved, okay? It's actually moved to high frequency again. Now, that doesn't make a lot of sense, I'm sure, but okay. But just the way to look at this is this. It's going to be important for us to put in an extra pole, and we'll do it by making this capacitor very large. So this case is interesting. Okay. Now, what happens when we make that capacitance very large? If we look at these expressions that I had right here, if this CGD, I'm going to add to it a compensation capacitor. So I'm adding another capacitor in parallel with CGD. So that means this term here gets to be very, very small, because this is, you know, so we're seeing this other pole show up here now. And what happens is, if you look at this, R out in parallel with Rn and parallel with 1 over Gm, if 1 over Gm is very small compared to these two, then we're ending up with something that looks like Gm over C sub G. Or 1 over C sub G times 1 over Gm. In other words, we're seeing an impedance of 1 over Gm and a gate capacitance of Cg when CGD is very large. So that's the case to think about. So let me just draw that. So here's the case I'm looking at. Let me just simplify it right now, not show all your stuff. I'm saying I got a gate capacitance right here, C gate. And actually, let me put this drain capacitance in here now, and I'll just give you the answer to this. I'm putting in another capacitor in parallel with CGD, and let's call this C sub C for a second. I'm making this get larger and larger. Okay? And here's what happens to the poles. Now, this is this S-plane plot, right? So I'm plotting the real axis pole, 1 over RC. That's a real axis pole, right? And there's two of them, as we saw from our exact analysis. There's one associated with this 1 over Rn. Let's make an Rn here. Here's our Vn. Here's 1 over Rn times C Miller. C Miller is equal to C sub C times the gain of this stage, and let's say the gain is Gm R out, right? Which is equal to RL, and R out equals RL in parallel with R0. So this is the old problem we've just worked with all along. Okay. So as I make C sub C larger, and C Miller is proportional to C sub C, this pole is moving in this direction, right? This number is getting smaller and smaller. Now here's what's kind of strange. As we go higher and higher, make this capacitor bigger and bigger, so this is C sub C increasing. There's another pole, and it started off out at 1 over R out C sub GD, okay, minus that, starts out at this, but as this gets smaller and smaller, it kind of turns into this pole, and what happens is this thing goes out further and further, right? And you end up at a location of, let me see, I got this here. S 1 over C sub G times 1 over GM. So in fact, let me jump over to this case. So this is the case I'm kind of talking about, and I give sort of these results here, okay, right? And there's a bunch of different limits we have to sort of look at, okay? And for whatever reason, I use C mu. I'm sorry, let me, why did I do that? I don't know. Let me just finish this answer, then we'll look at this summary results. So here's what's going on. This is a really important case, okay? As we make this capacitor bigger, it's Miller multiplied, so there's one pole that's going to a lower and lower frequency. But as we make this capacitor larger and larger, so it becomes it has a low impedance, a lower impedance than CD and CG. That's what we're comparing now is impedance levels. 1 over J omega C sub C, 1 over J omega C sub G, and 1 over J omega C sub D. And in the situation where this becomes so large that its impedance is a lot smaller than these two impedances, look what happens. Let's take C sub C to infinity for a second. That would be just like we had an impedance of 0 ohms, which would be like a short circuit. Okay? So that means I'm shorting the drain to the gate at this very high frequency with a very large C sub C. Okay? Now, if that's shorted, what's the resistance that I effectively see? I see RL in this direction, but what do I see looking down? It's a diode-connected transistor. What's the impedance of that? 1 over GM. And that's where it's coming from. Now, it's not like you can just sort of say, well, here's the voltage divider, or here is the output impedance I'm talking about. So this is a little bit more abstract than the argument I'm making here. The real justification for it comes from this exact analysis that you can do with this. Okay, so if you want to work it through once, solve the cubic, get the answer, you can believe these results, okay, right? But here's what I'm sort of motivating you here is what's happening when we make C sub C at infinite size is that we're effectively shorting out this gate to drain, and this transistor becomes a resistance of size 1 over GM. So what's happening is this pole, which starts out at sort of 1 over R out times the capacitance on that node, CGD, plus C sub D, be something like that. That's where it starts off from. Ends up going to be equal to 1 over GM times C sub G plus C sub D. In other words, these two are shorted together, and it's this capacitor plus this capacitor. It sees a 1 over GM. So we increase this capacitor, the poles split. This is called pole splitting. One pole goes to a low frequency. That's the Miller multiplied input pole. And another pole goes to a much higher frequency. As you increase the size of this capacitor between here and here. Normally, C sub G is the CGD is pretty small. If you haven't made it bigger by adding an extra capacitor there, it's fairly small. And then we're kind of in this limit right here. 1 over R out times CG. It's sort of the output resistance on this node with the capacitance that's hanging off that node. You know, maybe CGD here. So you're sort of in this limit when CG is small. But then when this gets really large, you kind of move over to this other limit, which is 1 over GM times CG plus CGD. You might say, geez, how does it go from that to that? Well, it does. Looks. I mean, just work it out in longhand. You can run SPICE. You can do whatever you want to do to convince yourself that this is true. But this is what happens to poles if you change that size. Okay, so what I did was, for this case, this inverter, and this is what makes these problems kind of difficult. Let me just motivate why I went through 3 different cases depending on the relative values of the time constants. And here's why. So let me just give you motivation why it's not just some simple answer, even for this really simple, our simplest circuit, good old inverter, right? Just think about this. Let's think about another limit where, so let's have an Rn. Let's have our CGD here. And here's our capacitor here. So the voltage divider one, right, from here to here, and this is CG, will be Rn, right, plus C sub G, plus C Miller, right, which is CGD times the gain, right, which is GM. Let's just say RL is much, much less than R naught, so it's GM RL, okay? So this is the C Miller, this is the C gate capacitance, right? And this is the input here. So this is kind of a little voltage divider, okay? So that makes sense. So we have a time constant of pole be at 1 over Rn with these capacitance here. Now let's put a really big capacitor out here. Let's make this capacitor huge. Let's make it large, just like we did the CGD thing. Let's say we make that so big that's at a much lower frequency than where this pole is. In other words, the pole at 1 over RL times CD plus CGD, this output pole, this is kind of omega out, okay? Let's call this one here, omega in, is 1 over Rn times CG plus GMRL times CGD. Okay? If omega out, because CD gets so big, maybe because the next stage you have has a big Miller multiplication, might be a reason why that might happen. If omega out is at a much lower frequency than omega in, do you see a problem with our Miller multiplication model? This GMRL here is the low frequency gain, right, of this stage. When I say that CD is getting really large, what am I doing? I'm saying that this, let's let CD be infinite for a second. If CD is infinite, what's the impedance on this node? 1 over J omega CD. If CD goes to infinity, it goes to 0, right? So that means this becomes like a ground. This is like a ground. What's the Miller multiplication effect going to be? And here's good old CGD. It goes from this point up to a ground. There's no gain. There's no multiplication, right? So if this time constant of this output pole is much, much lower frequency than the input pole, the gain is going to be killed for this input pole, and we won't see the Miller multiplication effect. This is 1 plus this, right? So this part here will go away. So we'll just end up with CGD. I should have left that in there. This is CGD times 1 plus the low frequency gain. That model at approximation is really wrong if these time constants aren't quite right. And quite right means normally in order for the Miller to work out, it has to be omega out has to be much, much greater than the input pole. In other words, this The roll-off on this input side will see the full gain of this stage. It will not be reduced because of a large output capacitance, which might reduce this gain. So we'll see really A0 as far as input side. If, on the other hand, this capacitance is huge, and this limit holds, the gain's killed, and we won't see this Miller multiplication effect. You see that? You get that relative values of time constants? So this is why we can sort of go after the low frequency pole, because you can sort of figure out a lot of these kind of things. Well, this pole is really a low frequency. This is much lower than this one, so I can approximate it. I mean, every time you find a pole that's at a really low frequency relative to another one, maybe here's kind of a rule, okay? If you find one pole that's at a really low frequency relative to another one, let's call it the low frequency pole and the high frequency pole. The low frequency pole, the node associated with that low frequency pole will appear to be like a ground compared to the high frequency pole. See what's happening? Because what's happening is the capacitances are so large, they're just their impedance values are at a very low value, and so that effectively that's killing that node. So effectively, you can pretty much take that kind of an approximation. That's pretty, how does that really play out in the real world? Okay, well, I mean, in terms of real examples. That's what I tried to do. So here's this inverter case. Now, I did a little change of variables for you here. Not nice. I actually used bipolar capacitor values. But C mu is the same as the CGD we've been talking about. C pi is the capacitance from the gate to the source, and CD is the capacitance from the drain to the source, okay? So this is the case I'm sort of looking at. If Rn times C pi, which is the Rn C pi time constant, and the R out is equal to RL in parallel with R0, so it's the output resistance times CD time constant. If that's much greater than Rn times the Miller multiplied value of C mu, okay? In other words, these are at a much higher frequency. So this time constant is very small. The Miller time constant is very small, right? It's much less than this, right? Relative to these two time constants. So that means the poles associated with these are very much. Is this right? Oh, this is backwards. Okay, this is okay. This is the case where Miller is not important. This is the case when the Miller pole is at a much higher frequency. That's what I was just talking about. This is much higher. So these time constants of Rn and C pi and RL and CD are at a much lower frequency than the Miller pole. So effectively the Miller pole there's no gain across it. Okay, the gain is killed by the fact that this RL CD thing is so low. Okay, so you end up then, it's like the C mu is not there. You end up in the limit of 1 over Rn times C pi, that pole right here, and RL times CD, or R out times CD. See that? So this is kind of a limit of C mu being really low, but being very unimportant, being a very small value, a very high impedance, or a time constant that's very high impedance. You can't just look at the C values. Now here's what really kind of, you think, well, geez, can I just compare the different C values to figure out what limit I'm in? No. It's really the time constants you got to look at, right? It's the resistance driving the capacitance that's really important. So you have to look at the time constants, all right? You can sort of see if this was 1 farad, doesn't matter what resistance probably in any reasonable circuit, that'd be in a limit where this is very big, right? But you generally got to look at these time constants to make this work out. What's the bottom line justification for this? You just got to work it out once if you want to, right? Solve these cubics and sort of see what happens to all these poles. I mean, I can try to give you a little insights into what's going on, and maybe looking at the limits is the way to think about it. What happens when C mu is small? That's the case right here. If C mu is small, certainly this is true, right? If C mu is small, you can sort of see there's two time constants, a voltage divider and this output impedance reduction thing. Let's take the case where CD is really big. This output CD is really large. What happens then? R out CD is a really big time constant. It's much longer. That means the pole associated with the output will be very low impedance. You end up with this case, 1 over R out times CD, and the second pole is at 1 over Rn times, this is like a ground, so it's this plus this with this Rn. This is where the pole is, second pole. The third case is what I just talked about before. That's the pole splitting case where C mu is really big. Then things split into this. 1 over Gm times C pi plus CD. So that's this plus this. Seeing this is like a short circuit here. And 1 over Rn times 1 plus Gm R out times C mu. That's the Miller multiplied pole. So it's the Miller multiplication case. All right. That's not easy. I will grant you that. All right. All right. Fortunately, we're usually in kind of this case. Well, it could be any one of these cases. You just got to check time constants. Right. So this little summary here is pretty important. If you can understand this summary, I think it'll help you understand what is going on with this relative values of the time constants for even a simple stage like this. But this is a really important case, right? Because this drives another case. This is what your homework's all about, right? That's the first part of it. Any questions about that? I'll have to take a couple of minute break. That's pretty tough stuff, so I'll sure. Yep.
Question with respect to like some of this other stuff.
Mm-hmm.
Like in like 120 and stuff, we talk about like stability with respect to like the poles, like poles all being
Left
inside
up.
the unit circle or whatnot. Or wait, not unit circle.
That's
Sorry,
Z transforms.
Sorry. So like, does
Left
that
half plane.
also like apply
Yeah.
here as well? Like,
Yep.
I really don't know.
Left half plane. Yeah, the left half plane.
Left
Pole-
half plane,
right,
right?
so-
Not unit circle.
So poles will need to be in the left half plane. And what will happen when we put in feedback, these poles will start to move into the right half plane, and that'll be the condition we will use to check for stability.
Okay.
Fortunately, we generally work with only real axis poles, so our condition is pretty simple, and that's what I'll use. So, but same stuff, simplified, the simplest possible version of it. Sure. No, I don't. No, the TA's got them. So yeah. So. Can you? Yeah. You can if you can't make. You can if you mail the TAs and tell them they can bring it to both discussion sections if you can't make the other one or something like that. So, yeah. Didn't want to lose them. Okay, let's roll 'em. Okay, any questions about this inverter thing? I'm going to now do the source follower, which is a little, it's actually a lot harder. Okay. Source follower. Okay, so we can do this one. There's two ways we'll do it. One, we'll sort of get roughly what the answer is, and then we'll drift through the notes pretty quickly because you can go through that. It's worked out in fairly gory detail there. But you should be able to get a good part of the answer from what you know now about, Miller and capacitors and all that kind of stuff. So let's take this case right here. All right, so now what is the capacitance on this node? Okay, there's a CGD, okay, going from here to here. Let me do something here, just before I guess I don't forget. I'll go back to this in a second, but let me take one other case just for a second for you. Make sure you got this right. Okay, this is the full circuit. Okay, RL with the diode connection for a current source, let's say down here. Okay. What about the pole associated? Is there some pole associated with this node right here? I seem to be only working where the V in and V out is. Why don't I worry about other places like this? Nothing's changing. There's no small signal. Remember what we're trying to calculate. We're trying to calculate the transfer function. H of omega, is V out of omega over V in of omega. That's what we're trying to do. So in other words, for a change in V in, what happens to V out? There's lots of nodes in the circuit that never see any change from V in. So therefore, they could have no effect on what this output voltage is going to be in its frequency dependence. This node right here is a bias node. It's a DC bias node. There's no small signal value appearing at this node here. The gain to this point is 0, right? From input to this point. So you can throw out any node that it's not in the signal path. That's not directly, there's a single path which works through all our circuits. You find that signal path, and only on that path is it important that you look for poles. Okay? So this here, there's some. In fact, often what we'll do is we'll put a big coupling capacitor on this node to make this node have less noise on it. Right? We'll put a big valued capacitor here just to make this so it appears like an AC ground. So that might be some reason you might look at the pole in there. You want to make sure but that's talking about a transfer function from the supply, right? There might be some noise on the supply. We want to sort of filter that out. So we'll do that by putting a big capacitor there. So then there's a transfer function from supply to that node, which then can get into our circuit. But as far as this kind of transfer function is concerned, you never have to worry about anything other than what the signal path is. Okay? All right. Let's back to this case now. Okay, so let's say this is the output resistance of this current source down here. So we have a CGD up here. We have a CD on this node going to ground here. What about this capacitor? Is this important to us? No, it's tied to a AC ground, right? The supply. So we don't even have to, that'll never show up in our answer, right? Because it's just tied to ground all the time. So you can simplify these capacitor things a lot, right? And with Miller multiplication, you can get everything down up to ground. That's kind of the trick, okay? What's the other ones? There's one here, CGS. Now that's a pretty big one. And it couples from the input right to the output. So that's what makes the source follower a little bit tricky. There's this CGS going on, right? There's also a CGB, right? Okay, so we're going to CGB. So there's the equivalent capacitor on this input here is going to be CGB plus CGD, because this is going to a ground, right? There's an AC ground up there, plus this CGS thing. Now, is this ground? No. This is the output. So we have now a case where we have gain across from here to the output. Now, if this was a gain of 1, we talked about that case before, if this voltage goes up and this voltage goes up, you know, this is like 1 minus A, right? And then A, if we solve the equations here, this would be this effectively C Miller associated with CGS, right? It's minus here because it's a positive gain, right? So if A is getting nearly 1, 1 minus 1 is 0, C Miller for the associated with the CGS is equal to 0. So we don't see this capacitor at all. To the extent that A is not exactly 1, we can plug in. A is equal to 1 over, is equal to GM, approximately, right, over 1 plus GM RS, if this is RS. Forgetting the tying off the substrate to the source. We take 1 minus A, plug in there, what do you get? You get 1 over 1 plus GM RS. Okay? Take 1 minus this, and you'll end up with this. So if I want to use this Miller multiplication for this gain that's nearly 1, okay, I'm going to end up with CGS time over 1 plus GMRS. And to the extent that GMRS is large, CGS is reduced in its importance. So the Miller multiplication effect on a source follower reduces the importance of CGS. That's important for us. Why is that so important for us? Why do we want to use source followers? They're buffers. We'd like to make that a big transistor sometimes so we can drive something. Look what's happening here. The capacitance, the worst capacitance, the CGS of this potentially very big transistor is reduced in size by this 1 plus GMRS factor. So it makes the source followers an even better buffer. Now, I'll tell you why that's happening. I'm not going to prove it to you right now, but it's negative feedback. A source follower is actually negative feedback. Okay? And I told you negative feedback makes everything better, right? Here what it's doing, it's making the input impedance higher, which is what you want. So negative feedback generally works things in all in the right direction, and here it's doing it for you. But we'll explain why it's negative feedback. But right now you just look through and see the hand calculation. You don't have to treat it as a feedback network. You can see that this CGS, this really big capacitor here, is getting reduced in its size. Okay? Everybody see that? See what's happening here? Important case. Okay? Now, if we have CS coming off here, you can see what happens as you go up in frequency here. Now, here's an interesting problem. What happens if CS gets, or we have a very large capacitance? Let's tie this to a big C load. Okay? So we have a huge capacitance on this node here. What's going to happen? If this node has a very large capacitance and this becomes shorted to ground, what happens with this CGS? It was really reduced in size right here because the gain from here to here was nearly 1. If this is a really big capacitor to ground, like a really big load, what's the gain from here to here? It gets much less than 1. It gets down towards 0, okay? So you see what's going to happen? As far as this inputs pole is concerned, we're going to see CGS, the effective Miller capacitance associated with CGS, to get larger. Right? So in other words, putting a load capacitance out here kills the gain of 1, makes CGS appear larger, so that'll make this input pole do what? Go to a lower frequency. So if we plot this thing, right? So in other words, what's going to happen, this pole associated with CGS is going to go to a lower frequency. Right? So you can sort of see there's a lot of, even though these are pretty simple cases, you can sort of see the coupling between these various stages, right? So that's kind of how I analyze this thing in your notes. Now, again, I did the same thing I did before. Hope this doesn't confuse you. I took off the C output, this node connected to the output here. Whoops, not here. One to ground here. I took that off and analyzed this thing, okay? Just because even with that, I'm sorry, you couldn't see that probably. I took the capacitance off the output and analyzed this case with just a C pi, okay? Even with that, it gets to be a big mess, right? Right? Then I redid it again. So the purpose of that was just so you get a little feel for what's going on. Then I redid it, including this output capacitance here, the CSB, which could be C load as well. Then I solved this whole thing, okay? You get this, all right? Then you mess around with this. What you can do is you can sort of say, okay, I have, it's a two-pole system. I can, 34. This is 1 plus, the denominator I can, it's basically, I can have it 1 plus j omega over P1 times 1 plus j omega over P2. I can multiply that out, and I get this. So that means that this term right here is equal to the sum of 1 over P1 plus 1 over P2, and this is the product of P1 and P2. So I'm using this to kind of do the quadratic formula in a simplified way, okay? And from that, I end up with poles, 2 poles. Okay, and the 2 poles are here. This is pole P1 and this is pole 2. Of course, I'll ask you to memorize these for the final. Not really, right? This is even too much for all of us. Okay, so I don't remember these at all, right? I mean, okay, so bottom line. What I do remember is the limiting cases that I have here for you, okay? This is what we use SPICE for, to do this really accurate intermediate points, right? But for just understanding what's going on, I got to look at these. I can look at the limiting cases. So there's 2 cases I'm really interested in here. The case when the output resistance times CGS plus CSB. This is, in other words, we have a very large value for this output, and we end up in this where this is kind of the case where the Miller multiplication works. CGS is being reduced by this 1 plus GMR S factor. So this is kind of where the Miller multiplication thing's kind of working, and it's helping you out. It's making CGS appear small, so this first pole is at a higher frequency. Case 2 is when the Miller multiplication thing is not working anymore, okay? And for that case, we have the output resistance is, we fully see the CGS plus CSB, and it's the output resistance that I'm worried about here, right? So RO is what? RO is 1 over GM in parallel with RS. So what I'm seeing here is this is going to be equal to 1 over GM parallel with RS. Because we're looking up into, remember what we're doing here. We're looking at the capacitance you can sort of begin to see something I'm doing. It's not, although I gave you the voltage dividers and output impedances are dropping, and that's kind of what's causing all these poles to show up. But you can sort of see a simplification that you can begin to make. You'll find a node. You look at the resistance, what's happening on that node, okay? Looking up, what do I see? I see 1 over GM. Looking down, I see RS. That's what R0 is. It's 1 over GM in parallel with RS. So that's the resistance on that node. Then I look at all the capacitance on that node. For this case, it's CGS. This is CGS plus CSB. So this is the capacitance to ground. And for this limit, I kind of view this as kind of looks like a ground here. So as far in this limit's concerned, it's this resistance with these two capacitors. So these various limits are kind of figuring out what the other sides of these capacitors are connected to. And sometimes they may be what the other sides of some resistances are connected to. That's what these limits are all about. All right, and this is times CGS plus CSB. So one is, it's the input resistance times its reduced value CGS. The other case we have is when this output is dominating, it's killing the gain. So that means this pole is a much lower frequency than this one. So there's two poles associated. I'm just looking at which of those two poles is the dominant one, and I'm just looking at those. Figuring out where the second pole is a mess. It's back to these formulas. So I'm only going after the lowest frequency pole here. It's sort of, it's the case when the output's dominating, when the gain is being killed by the output capacitance, or it's when the input's kind of dominating, and we really see the gain of 1 and we see this reduction of CGS because of the Miller case. Okay. I think the way to go after this, I mean, you can look at this math here, but that's not very important. It's not very useful, and just, it's a motivation. Go after these limits. Understand why these limits come out the way they do. Get a feel for why these limits do what they do. If you have questions, I'll go over this more. Let's do the third one. Common gate. This is in your homework, or in your homework. Common gate. Here's good old source resistance. Here's CSB, source to bulk. CGS now, the gate goes to ground, right, in a common gate. So CGS goes from here to ground. CGD goes from here to ground, gate to drain, and the gate's grounded. So, and C drain to bulk goes to ground. Look at this. Isn't this very interesting? And this is why common gates are really interesting. It's why the cascodes are interesting beyond what we saw already about increasing the output resistance. Notice, here's the gain from this point to this point. All the capacitances go from the input to ground or the output to ground. There's no capacitor coupling from the input to the output of any significant size. If you lay out your circuit in such a way that you actually introduce some capacitance by having some lines cross each other, you could really hurt yourself, because normally there's no capacitance there. And if this circuit has a lot of gain, you get Miller multiplication. But since there's no capacitor, we do see no Miller multiplication of any gain right here. So this is really neat. So what's the poles of this one? Really simple. Here's the voltage divider on the input, so the input pole will be 1 over RS times CS. And the output is the parallel combination, the output impedance. So it's going to be an output pole at 1 over RL times CD. The input and output are decoupled. Really nice. Okay. Okay. Now, whoops, wrong here. Uh-oh, I slipped up on something. Someone should have caught me. What's wrong with what I said here? This is important. If you can see this, you've pretty well got this stuff knocked. What did I say? The easy way to figure this stuff out is to go after the resistance you see at the node and then the capacitance you see to ground and multiply those two together. Okay, now, let's do that for this circuit. What is the resistance that I see at this node? Parallel with what? Looking into the source of a transistor is what? One over GM. Right. So this should be RS in parallel with 1 over GM. Now you can work this out. You know, that's what I did here. I did KCL and KVL and worked it out, and here's where the two poles were at. 1 over RLCD and 1 over RS in parallel with 1 over GM times CS. Effectively what's happening is, there's the voltage division. We're talking about a voltage divider here, right? So we have a resistor of 1 over GM, here's an RS, and here's CS, right? So we're trying to figure out the voltage divider from, let's call this Vn prime. This is Vn prime. So it's the voltage division between here and here due to the fact that this capacitance here is increasing, or Vs, I guess they're called here, right? Let's call it Vs. If you have a resistor on this side here, that changes how that voltage division works, right? Because there's a resistance on that. So you work this problem out, and you will see that the pole ends up being at 1 over GM in parallel with RS. Okay, so work out this problem. So it's just a good old voltage divider again, and it just has to do with the impedance looking into this node right here. It's part of it, it's the answer. Okay? Now, that's really good, right? 1 over GM is a small value. So in other words, we've become very insensitive to this capacitance hanging on this node here. So that's good. So now let's do another circuit. Let's put two circuits together. Let's take a common source, and let's make it a current source. Let's just have lots of gain, okay? Let's have an R in, our source. Here's a V in. So lots of gain from here, and here's our CGD, right? So I'm going to see a gain of, let's say it's a perfect current source, I'm going to see a pole on this input side here of 1 over R in times CGD times 1 plus GMR0, right? Where this is R0, this guy. Right? Lots of gain. Boy, I'm gonna have a real problem on this input node if this is a big value resistor. What can we do here to change all this? Here's what we can do. Let's put a common gate right afterwards. Let's do another current source load so we get lots of gain on this stage as well. What's the gain from here to here? Low frequency gain. Gain from here, let's start right from here, okay, for a second. Okay. Well, from here, it's fine. Low frequency gain. From here to here is going to be what? GM, let's call this transistor 1, let's call this transistor 2. It's going to be GM1, R01. That's the gain from here. But what's on this node right here? What's R01 in parallel with? Parallel with 1 over GM2. Okay? So the gain from here to here is going to be what? Approximately 1. So we no longer have a big gain from here to here. It's in fact approximately minus 1, right? So this equals minus 1. So what we're going to get here is what we're going to get instead is 1 over Rn times 2 CGD, transistor 1. So we get rid of the Miller multiplication of this input stage. Now, let's go from here to here. What's the gain from here to here? Well, the gain from, let's call this V out 1. V out to V out 1 is equal to plus GM2 times, sort of R out and R out 2. So it's R out at this node right here. What's R out at this node right here? Looking into here, we see a source degeneration. So we got a really nice big value. So this is really big in this bottom here. Maybe this is getting, that's not the point I wanted to make. This is going to be a little R0 up here. Let's call this R03. So this thing's going to end up being equal to GM2 times R03 in parallel with this big resistance looking back this way. So we get the full gain. So from here to here, we end up with good old GM R out, just like we want. We get rid of the Miller multiplication associated with this input gain stage right here. There is no Miller multiplication for a common gate, so we have no Miller multiplication problems. That's really good. So in other words, this configuration of a common source with a common gate is really good for high frequency performance. Well, what can I do here? Do I need this current source here? I got current coming from this path right here. Do I need another piece of current? Let's just take that out. And what is that circuit then? I start off with a current source. This is R03, right? I go into a common gate, which I ground. I go into my common source, and here's Vn, and here's V out. Whoops, here's V out. So what is this? It's a cascode, right? So you can see that a cascode has a really nice characteristic. The reason is because you don't have, there's no significant gain between V in and V out, any capacitance. Across the major gain, there's no significant capacitance. There's a gain of -1 from here to here, so that multiplies this guy by a factor of 2 instead of a factor of times 100 or something like that. And there's no gain, there's no capacitor from here to here, there's lots of gain. So no gain, lots of capacitance, or at least some capacitance. Here we have lots of gain, but no capacitance. So in both cases, we win. We don't see a big Miller multiplication factor. So this cascode is how you make circuits fast. If you look at the front end quite often of your cell phone, you will see a cascode. This is coming off your little antenna, all right? It goes into this first stage of your low noise amplifier. LNA is low noise amplifier. You want it really low noise because you're trying to detect a really small signal that's coming into this antenna. It's microvolts. That's what you get off an antenna. So if you have, every transistor has a little noise associated with it. It's got a little noise in series, okay, with your input. So you got to design this amplifier to be as low as noise as possible. We won't do a lot of noise design in this class. That's kind of a 240 thing, right? Got to leave something for 240 to do, and that's one of the things we have them do, okay, right? So low noise design. But basically, it's a circuit like this. Cascode it so you can get better frequency response. Sometimes you don't, but quite often you do. You can tune things out sometimes too. Yeah.
Why isn't there a pole associated with the intermediary node?
There is, but what's its? Good question. So what is its? What's the pole at this point right here? What's the resistance we see associated with the capacitors on that node? We're going to see an R0, 1, in parallel with what? 1 over GM2. So 1 over GM is a really low resistance value, right? And so even though there's capacitance on this node and there's a pole there, that pole's at a very high frequency. It's associated with this 1 over GM. To have a low frequency pole, it's not, what does it take? And here's why it takes two things to make a pole be at low frequency. It needs to have a high value of resistance and a high value of capacitance, okay? It's got to have both things. And a time constant, there's two things. It's an R and a C. If the resistance is really small, then the pole goes to high frequency. If the capacitance is really small, it goes to high frequency. If neither one of them is really small, then you're sunk, right? That's what you're going to have in your projects, right? You'll have lots of cases where you've got that internal node that most of you guys use a differential pair followed by a common source stage. What's going to happen? All right? You got that differential pair with really low currents, really high output resistance, right? It's going to drive that second stage, that common source stage. Could be a nice little capacitor there with a gate capacitance and so on. Not a lot of Miller capacitance probably. You didn't have a lot of gain in that second stage, but you're going to have a really high output impedance coming off that first stage. It's going to see that gate capacitance of that common source. And you made that common source pretty big too, right, in order to drive that output. So it's got a nice big juicy gate capacitance there, right? So when that gets hit with a nice large output resistance, you got a nice low frequency pole. Right? Easy to calculate. Not so easy to get rid of.